Okay. From now on, we have to use the online teaching to give you a lecture on organic lab. Next week, you perform or observe the how the experimental conditions being carried out by the TA. The experiment is experimental 3 with the Wittig reaction. Wittig reaction is very, very common and very important in organic chemistry to construct the double bond olefinic bonding between the carbonyl function and also one reagent is called ELI. This is the ELI reagent together. So there will be a component and a B component and keep them together become one single molecule with a fully conjugated. And the conversion will be a carbonyl function being changed to CC double bond. And because of this reason, pi electron on the exoskeleton be able to continue conjugate onto the carbonyl function here. And as I indicated to you before, the electron activity of the oxygen is higher than the carbon, so that electron is going to pull out of there. At the time that the exoskeleton is pi electron rich, so they will be pulled onto this side, and that's what we call push and pull. And when you have a molecule in such configuration, it tends to absorb more on the UV visible wavelength, and that's the way you can see the change of the optical absorption from this side to that side. Or this more like a two or more chromophore type of the photo characteristic in there. But in terms of the chemistry, the TA will give you the starting material and also the ELI, the molecule. You just mix them together, making the reaction. And the reaction will not, in this particular case, will not use any solvent. But both are solid in principle at the room temperature, right? You may ask how the reaction can go with each other. The solid cannot react with the solid. So you heat to 110 degree or 150 degree above the melting point of the starting material, so it's more like a liquid, right? thick liquid. And once it becomes a liquid, you'll be able to stir on the mixture, and that the molecular contact with the ELI reagent, the reaction will begin in that. Right? Now, first is this. Because the TA gives you the reagent right away without prior preparation, in case of the graduate student, they have to prepare themselves. So I will give you the chemistry, how to prepare that. Actually is very simple. It's not very complicated. It's an in situ reaction. The reaction just simply, for example, this ELI is the starting material should corresponding starting material will be alpha bromo ester. And so simply mix 1-to-1 ratio of the triphenyl phosphine with this halide. It can be a chloride, it can be an iodide, it can be a bromo. The bonding, they all work in such a way. The reaction occur in such a way that driving force comes from ampere electron of the phosphine. This is as like a nitrogen before, right? Nitrogen has 2 ampere electron as well. In the periodical table, phosphine is right below the nitrogen. So the same ampere electron has a driving force to donate it onto this carbon, and that will make a higher electronegative the bromo to move out. Right? And one of the reasons this bromo is more active than the normal archaeal bromo is because of the carbonyl group here, and drawing the electron toward this way, and that will pull some electron density along with it, right? And that will make it more susceptible to the cleavage. That's why we call this alpha bromo is more reactive compared to the archaea, the bromo, and that's also a reason to form this can be quite rarely to occur in that. And once it happens, covalent bond will be generated between the phosphine and the carbon, and because the ampere electron given out, so it will be a positive charge on the phosphine. And once that happens, take a look at these two protons. One side next to the carbonyl electron withdrawing the group toward the oxygen, uh, and because the electron activity higher, and one side with a positive charge on that, so that will make um, these two protons much more acidic. That's why we call acidic the alpha proton. So because of that reason, it can be neutralized much easier with a weak base. The alkoxide is not a very strong base, sufficient enough to take this proton and move the bonding electron onto this carbon, and that will generate the anion here. And for the structure wise, you can draw this form like a Trojan ion, or you just draw a double bond here. Both are okay in the structure, right? Uh, and once this the carbon ion here negative charge on the carbon is called carbon ion. Once you have a carbon ion is very reactive. They are very nucleophilic, means that they can donate out the electron very easily on that. So that once this form is all given for your reaction, when you stir them together, uh, this anion is going to attack on this carbonyl carbon, and for the same reason as I explained to you, because of oxygen electronegative, pi electron tends to move toward the oxygen, and that will lead direction of this ampere electron to this carbon, and that form a covalent bonding between them, and because the oxygen pick up a pi electron, and you have a negative charge on there. And here will be a single covalent bonding, single covalent bonding. In principle, there will be a rotation here. But once they rotate it in certain way that this negative charge see the positive charge, they're going to be neutralized, and that's a new nature action it will occur. Once it neutralized, forming the bonding, it will be a four-member ring. Right? Take a look at this four-member ring. In general, the carbon is a tetrahedron angle is 109 degree, and the four-member ring is 90 degree with each other. Right? So it shifts from 109 to 9. That's very, very strange. It means a push toward this way and this push that way. They bump to each other very much of it. And that's one reason. And the other, consider the size of an atom. The phosphine is much, much bigger than the carbon. So they are very crowded. Steric hindrance is very much occur here besides the strain on this angular strain here, and that will make these four memory very, very unstable. Once they fall, they can easily break off on the upway, right? In nature, it will happen that way. Now, which way to break? You can break it this way or break it that way. Right? Then you can see that because the phosphine tends to like oxygen much more than the carbon, and that's the reason the oxygen will be linked onto the phosphine. And if you link it this way, of course, this bond is going to move here, and that gives you a double bond with the phosphide product. Right? Now take a look at the this 4p. It has how many bonding around it? It has a 1, 2, 3, 4, 5. 5 bonding, so contributes 5 electrons here. So this phosphine is oxidation state is +5. Now, you come back to starting material or triphenyl phosphine. You have the 3 covalent bonding on it. So each one has a covalent electron. So the oxidation state of the phosphine is +3. So you are actually changing from the +3 to +5, and that's called oxidation. So phosphine itself oxidized to phosphide. So once this reagent been oxidized, then the starting material has to be reduced, and that's the reason with oxygen on the carbon is in a higher oxidation state. So you come to the same double bond with carbon-carbon, there's no oxygen. So it's a low oxidation state. And so this is reduced from the that from so one side reduce oxidize, the other side has to be reduced, and that will balance out all of the electronic situation in here. Now, once you know the reaction mechanism, now you see that the uh, the melting point of your product is supposed to be 80 degrees Celsius. Uh, at the end of the reaction, the temperature is 110 degrees, so it's higher than that. So this is supposed to be melt into more like a liquid, and likely to be a thick the liquid on there, right? In order to work it up, you have to cool down to room temperature, and that will become a solid. And it will not be a powder, it will more like a cake, heavy, thick, dense cake on that. Right? How do you take it out? And first of all, you have to separate out from the byproduct, which is the powder. Uh, so we use heptane to make extraction on the product. Turns out to be the product is more soluble in heptane than the phosphate. Uh, this is much insoluble in the heptane, so you can differentiate between them. So extraction will be 2-3 portions. So don't use too much heptane to begin with. Separate into 3 portions, so you can extract the first time. It means some of the product may still scramble together with this powder, right? You have to take a time to get it out. Use a spatula, keep it stirring or breaking or whatever you can do. Hope that all of them, all the hidden inside the solid will be able to dissolve out at 10. So once a 2-3 washing, you combine all the wash the solution together and the evaporate at 10. Now you get more like this product. So the product will not be easily seen as a solid, right? Even though the melting point is 80 degrees, it may be more like a thick paste that you will see, right? And that's the reason you need to precipitate or recrystallize from methanol, and that's what you're going to use. So you add methanol, it will dissolve, and then cool down as you do before. You know how the procedure will go to recrystallize. But I want to remind you one more time again. Uh, don't use too much methanol because the compound does have a solubility in the methanol. The more quantity, volume of the methanol you use, the more loss you're going to observe. Right? You may not get 100% yield out if you put too much methanol. And besides, you will need to cool down to a low temperature, 5 degrees with ice, to reduce the solubility of the product in the methanol. Right? And that's what you're going to do. Once you follow this procedure and get the product, and then of course next step would be identify besides measuring the melting point to match how much how much deviation that you have from the theoretical melting point, and that would be tell you how the purity you have, right? And the other is spectroscopic identification is more important for you to verify your structure. One is IR, the other is UV visible spectrum. As what I told you before, the IR, you should be able to know that the difference between these two structures is very obvious. Is the disappearance of the aldehyde, and we know the aldehyde right next to the benzene and the type of the moiety, the infrared absorption supposed to be 1690 Wim number, and once that should disappear, and the new component come out will be the ester function, and very very easy to see because this harmonic absorption is very very strong and standard at about 1725 wave number. And besides that, it will have also CO, the CO vibration, and also COC vibration. All these focus around region of 1100 to 1200 wave number. So you should have a two multiple peak in here. In this, that's why I say CO on one and the COC also the other one, and there, and so this region should between the 110 to 112, the 120 the 1100 to 1200 wave number region, you should see that those peaks. Of course, the CC double bond will be a 1600 wave number, but they will mix with the aromatic, so we may not be able to differentiate on that. And that's the main IR differentiation. The other is the UV visible. UV visible, you can see the once you link the double bond here, you have an extend, as I indicated earlier. There's an extension of the conjugation with the push and the pull function. So the optical absorption of UV will shift from about this region, about 300 nanometer to 380 nanometer, of course, to 400 nanometer. And you can see a ray shift, that's called ray shift, to the longer wavelength, ray shift, because of extension of the extended conjugation. So the infrared is more, it's very, very crucial for the functional group change. But UV visible is very crucial for the conjugation, and that's the reason. If if you see the one peak around the 300 and the 380, and both exist, they're not it's quantifiable, the ratio between starting material and the product. Uh, so you can use that the extension coefficient, the peak heights, to exactly calculate the ratio between them and to know what's the product conversion you have. Right. The next one will be NMR. NMR is actually more accurate to pinpoint the molecular structure of your compound, and that's the reason I have to go through the NMR spectroscopy today with you. This is the diagram that I gave you before for infrared. This is a sentence I already include NMR spectrum here, and that other than the infrared spectrum, the NMR is using the radio frequency. It's very very low here compared to infrared. It's way way low there. So the energy is very very low. It's very very small. So how was it so small energy to be able to make excitation on the molecule? Of course, it's not possible for the molecule alone, and it's not even possible for the local structure like the functional group, vibration, or rotation. It can only make excitation like atom itself, right? And because of the NMR, you have several different atoms here, but the NMR is based on magnetic property, so it doesn't require the arc electron. So in that case, the only the proton has the I electron, and C13 has the arc electron, and the C12 doesn't have the even electron, so that is not the NMR active. So these are only two types. Of course, the proton is more common because all the organic compound has a proton. Right? So now, I will give you a very short description regarding to the principle of NMR. Is that NMR is measuring the characteristic of the proton nuclei in there. If you take a look at the one typical example of the organic compound, it does contains many different type of the proton in the molecule, and each proton has a different environment, right? And that's this difference in the environment does lead to a different of the nucleus in here, and that allow us to differentiate uh, one proton versus the other proton. And that's the principle, right? If you take the compound and dissolve in the chloroform D solvent in the NMR tube, you see all the dissolved molecule. You cannot do solid for the compound. You have to be fully dissolved in the becoming molecular measurement. Uh, so the molecule itself will tumble inside the solvent, right, moving around, and so there's no vector at all on each nucleus in here. But remember, all the protons, the composition in such a way that it has a nucleus, uh, and each nucleus has one electron, free electron go around it, orbiting around that with equal distance in the orbital, fixed orbital. And of course, the orbital is not only in this direction, can be in this direction, all around that, right? And according to similar to what you learn in the general physics, uh, they will tell you, or general physical chemistry, they will tell you if you have a electron orbiting around, all the current circulating around a ion, it will generate magnetic field, in a perpendicular direction. And that's called thumb rule. Means that you take your hand with a forefinger bending circle around this direction. You will need your thumb sticking out perpendicular. And that's the direction for the magnetic field. So you have an electric field around here. The magnetic field will be perpendicular to the electric field, and that's the nature outcome for in the universe. It does occur that way. Uh, and this magnetic field we define as a dipole moment in there. So you can see, uh, and this field, magnetic field, does respond to the external magnetic field because the NMR machine, um, it does consist of a big magnet, a megahertz magnet in there. So when you turn it on, even though this is a very tiny magnet, it will respond to external magnetic field to align around it, right? And once they align around it, uh, it will not be sit like a perpendicular, standing perpendicular to the the direction, the vector of the external magnetic field. Will not do either. It will be tilt most of the time, just like an Earth tilt orbiting around the sun. Right? Around the sun, it is a tilt, and itself also self-rotated. We have every day turning around, self-rotated, identical to the Earth's action. Even come to the atomic level, it will still behave identical phenomena in here. So once they are tilted in an angle and they self-rotated, it turns out to be rotating on this vector, on this deformation, and that's the rotation that we use to set the NMR measurement. And the NMR measurement, you see the axis as the x-axis is frequency, and which frequency is exactly this frequency. It's a pulsational frequency on each proton in there. And the frequency defined as how many circles per second, right? So it means how fast it is rotated, and now be the frequency you measure for the NMR spectrum. And this frequency is a function of the magnetic field, the total magnetic field. And there are two components of the magnetic field. One is external, you put it in, that's constant. That's constant. You don't change it. But the other one is the this dipole moment induced another one, because most of the nature phenomena in the physics is that when you apply external energy, make excitation from the ground state to excited state, to turn it on, uh, they don't like it, right? Once the system goes to the higher oxidation state, the higher state, if they come to the tendency is for them to go down. So they want to balance the energy to more minimum to reach the equilibration on that. So so it will be a object, the small magnet being magnetic field being generated, induced, that we call induced, and that's the one that allow us to differentiate uh, different protons. And so what happened is I say the NMR is based on that induced magnetic field. And this induced magnetic field will uh, de- depend on how much electron density around it. You can easily imagine that if more electron density around this nucleus, you're going to have a more induced magnetic field to balance this external magnetic field, right? And that's the difference between for us to differentiate different type of proton. And it turns out to be, forget about the principle and what you exactly see in the NMR is more electron density around that, you will see more downfield shift or upfield shift and against from each other, and that separate out each proton. And of course the table will give you a reference. More likely what type of proton will be sit where in that, and that's why you want to check on it. But at least you know where they come from. It's actually based on the electron density around that more electron density will generate more magnetic field, and then more magnetic field counter the external magnetic field, and that to reach the minimum of this, and that's exactly all the very simple, uh, very short description of NMR principle for you to pick up very quickly on that. Of course, for the details, much more complicated. Uh, and there will be three parameters you're going to follow for the NMR spectrum. The first one is the chemical shift, and the chemical unit is called parts per minute, ppm, parts per minute. And one reason parts per minute is because of this dipole is so small, right? You need a million. And measure is only the 1 millionth, right? It's so small. But then, how do you get into 1 ppm, 2 ppm? Because we use a megahertz, mega, right? So mega times the millionth become 1, or 2, or 3. And that's why 1, 2, 3 ppm on the spectrum you can you see. And that's what, but those are the frequency number, how many hertz frequency. Uh, that you doing it. So this is the first parameter. The second parameter is very, very simple. It's the integration ratio. It's exactly for the proton count. So each peak will give you, and machine instrument will give you integration ratio, and that tells you exactly directly how many proton for that particular peak is. So it's very, very accurate, and the ratio should be right, and you'll be able to count it very exactly. And the third parameter will be a coupling. The coupling for you at the moment uh, is for you to correlate, verify your structure. Of course, for the graduate student, this is a very, very important tool to build up the correlation on the entire chemical structure. But for you, it will be more like to verify whether your proton is what you see, right? And the first parameter of the chemical shift I tell you depends on the electron density around the area to create enough magnetic field, induce the magnetic field that to differentiate from different protons. So for this reason, most of the we are concerned is uh, concerning is the carbon, right? And the proton link onto the carbon. This is the proton NMR measurement. And the, the electronegativity between proton and carbon is identical number, 2.5. So that's neutral. There's no pulling or push. But once the carbon link onto the nitrogen, CN bonding or CO, you can see the electronegativity is higher here. So electron is going to pull toward that, and that will draw the electron density around this proton lower, and that will, the effect will be a shift, the chemical shift in some way. So what do we see in the general? How do you recognize, use the NMR? You can download or see such type of chart from the Google. Many different types that throw in. See, this is just give you one typical one. You can see that 0 ppm is what we use for as a reference. It's a TMS with a sided compound, uh, as a reference, and all the different peak is correlated to that in chip. So without knowing exactly the reason on that, you can see most aliphatic proton is going to locate it around the zero point 0.5 to the 1.5 this region aliphatic, because it's a simple carbon and hydrogen linked together. There's no electronegativity difference. So there, the chemical shift will be here as a base. Most time we use that as a baseline, and then once you change that the covalent bonding to the sulfur and nitrogen, more electronegative. Of course, it's going to shift it. This proton chemical shift because it lost the electron density on the also the local magnetic field on that, so it will shift it in this way. And now if you link to even higher electronegative oxygen, you shift it even more. You see, it's correlated to how the electronegativity linkage there. And also, of course, besides that, it may be the halogen or the CO or some other electron withdrawal group can shift them all around, right? And the other category will be a pi electron. The pi electron is the current of the ring current, which is the which magnetic field is somewhat different. That's the reason the CC double bond is most likely in the between the 4 ppm to 5 ppm region, because the pi electron itself separate out from covalent the electron, uh, and because the pi electron itself has a ring current on it, so their induced magnetic field center is not the same as the aliphatic. Uh, but no, regardless of what, the C double bond tends to be in this region, as I indicate. Once you go to the benzene, will be 6 ppm, and your insulfin will be most all the unrated proton will be around this region, between the 7 ppm to 8 ppm range in there, right? So it's very easy for you to see those peaks to identify, right? And here, I give you one of the one view graph that will indicate different numbers, precise number on the example molecules in there, and then you can see the chemical shape for each type of proton is different, and that's the reason the NMR is so powerful and so precise that you can pinpoint what type of proton you have and what the location of the proton next to the carbonyl group or next to aliphatic or aromatic type proton, all different chemical shifts. So if, that will allow us to verify different the structures. But the last parameter I say is the carbon constant. It is very important. It comes from the fact that you have this one electron orbiting around nucleus here, and it's nearby, only nearby. It's very, very tiny. This is a very, very tiny magnet. Right next to a very, very tiny magnet. Okay, two magnets that attract to each other, either repulsion or the attraction, right? Magnetism always go this way, either attract, and that's called coupling. So they can coupling to each other, talk to each other. Which way talk? Uh, they cannot talk to each other more than one carbon away. It's too far, and that's the reason it become very powerful that we can use the coupling to pinpoint exactly how many protons right next to me. Right? If you use that as a standard, right? If one proton next to B, it will be a doublet. If you two proton will be a triplet. If a three proton next to me will be the quartet. And how they count to that? The way to count it is very, very simple. If you have one proton next to A, and it will be the, the spin up, spin down the orbital. the splitting, right? When they couple each other, making excitation, it'll be a splitting orbital. It'll be a 1 to 1 split, become different nuclei, right? The second proton comes in for each orbital label is going to split further, alright? And because of the same type of proton, so the splitting distance will be identical. So this, it will go one here, and then go another one splitting again. And this guy is going to split also this way, right? This way. But then because of two go around with it, so sum it up, it'll be two. So the ratio should be 1 to 1. So triplet intensity ratio should be 1 to 1 ratio, and that indicates that the HA doesn't have a two protons right next to it. But if the case, if you have a three proton right next to it, you just keep going, another additional proton, and that will end up by this way. Two come here, two come this way, and one come this way, one come this way. So it will sum these two up will be three. Sum this up with three. But here remain as one, remain as one. So that'll be 1, 3, 3, 1 ratio, right? So three proton next to this. This peak, proton peak should see quartet with a 1, 3, 3, 1 ratio. So this is a very precise on the structural properties that you can observe in the NMR spectra. I give you the last view graph will be example, and with the ester group identical to what you have. So it should be in such a way that it begins from the first proton will be a methyl group right next to the carbonyl, because right next to carbonyl with the electron withdrawing from here, so you can see the electron density is this, right? So it will be downfield shift, and how much it shift, you can see here it has shifted to about 1.9 ppm, and the carbonyl like acetal is typically is 2.1 ppm for the acetal, so it's very very close to that, right? And there's no other proton right next to it, right? Because the most nearby proton will be here. That's far away. That's too far. Already two atoms away. That's too far. There's no coupling at all. So it's only single up itself. So be singlet. And the content NMR machine will tell you it's 3 content. So that'll be 3 proton match with the CS3. The next one will be this proton, right? This proton on the right next to oxygen carbonyl electron withdrawing much on it, and that's why this is a directly bonding withdrawing. So this proton shift the most, and most to where to almost 4 ppm, and the proton content integration. Proton content is 2. Insulin here is 2. So it means you have 2 protons right here. Yeah, it's that 2 proton, and this 2 proton next to 3 also 2 proton, right? So this the peak next to 2 proton, it should be what? Triplet, right? So it is a triplet, 1 to 1 ratio for the peak height for the triplet. And that's settled. Now come to here, a little bit more complicated. It's one atom away from the oxygen, right? So the shift will not be that much, become weakened, much weakened, right? Will not be as much as this one. So it will be now it's located at the 1.45 ppm, and the integration ratio tells you 2 also. So that's 2 proton, and the coupling, well, is multiple, right? Why it's multiple? Because it next to this guy with 2 proton will be a triplet, but it also next to here 1 proton, right? So be doublet. So this is supposed to be a triplet and a doublet overlap the split altogether. That's why it becomes a little bit more complicated, multiple peak, right? And the most complicated will be this proton. This single proton will be 1 here, but then in next to 6, total 6 proton 5. So it should be heptate. And but also next to two proton here should be a triplet. So this is single one, just one proton will split into heptate and then times times triplet. And that's why it becomes so broad. The hump in here and many multiple pieces here. So all this is very easy to count the structure and verify much more precisely compared to infrared or UV visible spectrum, and that's why NMR is most important structure verification tool for organic compounds. I hope that you get some idea about this type of the spectroscopy, and I will see you next week for experiment 4.